All right, good morning, everyone. What we're going to be doing today is going to be discussing the second portion of Unit 3, or I should say Lesson 14-2, which is the second part of Activity 14. Um, Within this lesson, we're once again going to be going over a lot of things that we probably have covered before. You probably have talked about radians. You probably have seen it all before. Um, but within this particular unit, it's going to be so important for us to understand and use that we're going to need to have another basic idea on this stuff. Okay. So once again, we are kind of building up. We're re-providing information for you to eventually be able to take this information and apply it to future problems that we're going to have. Okay. So the first part of this lesson is simply put, we have to discuss radians. Okay. Typically, how do we find radians? How do we work with them? How do we actually go from there? Now, if we were in class, we would actually talk about like what the whole idea of a radian is. Okay, to kind of simplify that concept for you, a radian is another form of measure where we're going to use an arc length to actually describe an angle measure. Okay, more often than not, you see radians as a typical sign of measure in math. And the reason is because radians are smaller. Okay. It's easier to simplify fractions. It's easier to make things look better when you're not dealing with very large degrees. Okay. For example, if I'm really thinking about it, 4 pi as one answer seems a lot better than 720 degrees, especially when you're trying to multiply, divide, add, and do all those things together. Okay. So that's going to be kind of one of the concepts you understand. The reason why we have radians, the reason why we use them is because using it with math is a lot easier. Okay. It's simplifying tool is a lot better. Okay. So first and foremost, let's talk about number 2 here. Okay. What is a complete rotation? Well, complete rotation comes around in a simple aspect. If that was a circle, oops, let me grab my pen here. A circle has a 360-degree total rotation, okay? With 180 degrees being one half of it. Well, in this concept, if we're dealing with radians, 360 degrees is the same thing as 2 pi, okay? Where if I actually find that value, I can actually simplify it and work it from there, okay? Now, understand if I want to try to like really work this out and try to figure this out, how do these relate to one another? Okay. Well, understand if I want to turn degrees into radians, I'm going to use a simple process and I can actually use these values to my advantage. Okay. Think about how they're related. Well, if I want to actually find degrees to radians, it's just going to be using pi over 180 to help simplify it. Where if you really think about this, if I were to take 360 and times it with pi over 180, 360 divided by 180 would just be 2, and the pi would just sit, giving me a value of 2 pi as an answer. So I can use this as my conversion tool for a lot of these values. Okay? So let's go ahead and work through that. If I wanted to convert these degree measures into radians, it would simply be, I would take 45 over 180. And then on top of that, I would multiply by pi on the top value. Okay? Now, 45 goes into 180 4 times, which means this would be basically 1/4, or this would be pi over 4 as a radian measure. Okay? Same thing over here. We have 210 over 180. In this case, we're going to have a mixed fraction. 210 over 180, we could basically simplify that down until we got 4 pi over 3. But since it was negative here, it's got to be negative here as well. Okay, I probably should put the negative 210 into there. Okay? And this value kind of works constantly, all right? Like the same thing here. If 15 degrees, I could take 15 pi over 180 and simplify that. 15 goes into 180, I believe, 12 times. This would come out to be pi over 12. So we can always convert into these values. And once again, understand the whole reason we want to use radians because this as a actual fraction would be a lot more complicated, or I should say even, excuse me, I should actually go back to the beginning. This number would be very complicated with very large values. Okay, if I had to start multiplying and dividing, it'd be very troublesome. Versus this one, I can use 4 and 3 in my head a lot easier than I can 210. So radians are actually a very nice friend to us because they can actually help us derive certain values from this. Okay. Now, that was kind of step one. We have to understand how to actually work that, but we also have to understand kind of how to actually graph it. Or actually, before we do that, let's just make sure we understand this other concept. If I want to convert a radian back into a degree, well, what I'm going to do is I'm going to flip that value. If I want to go from radian to degrees, I'm going to actually flip that and just multiply it by 180 over pi, which in reality is just basically canceling out the pi's. If I were to take pi over 2 and times it by 180 over pi, technically these two would cancel out, and this would just become 90 degrees, okay? And that's how we convert back to it. Probably not going to spend a lot of time on that, but it's kind of the idea, all right? That conversion rate works vice versa, okay? So now what we want to be able to do is try to understand graphing of a radian measure, okay? Because understanding quadrants, actually understanding all these different concepts are going to be huge in the process, okay? So let's say I want to complete 1/4 of a complete counterclockwise, or complete clockwise rotation. So if I'm here, we have our initial side here. Clockwise goes down, okay? So I'm going to complete down until I get to this point here. So my angle is currently this, initial side, terminal side, from start to finish. That's 1/4 complete clockwise rotation. Well, if I'm going to use that, I want to understand what's the radian measure. Well, in degrees, that would be -90. In radians, once again, I want to think, okay, well, what's that value? Well, if this is pi over here and one full rotation is 2 pi, then that must be half of that value. This is negative pi over 2. Okay? If I go 2/3 of a complete counterclockwise rotation, once again, we draw our graph. 2/3, where it would be right about here. We want to try to understand what's that actual value. Well, 2/3 would be 120 degrees. Once again, if you're trying to think about 2/3 of 180. Oops, excuse me. I was thinking of 2/3 of 180, not 2/3 of the whole graph. So let's kind of quickly go through that one real quick. This would be 2/3 of the whole graph, or in other words, all the way down here. Okay. Which would come out to be 4 pi over 3. Okay. That value is going to be the same as 210 degrees. So we can always reference back to these using this information, okay? Next, we want to talk about coterminal angles, understanding how can we actually value coterminals of each. Well, we talked about how with degrees, a coterminal is 360 positive or negative degrees from that actual value. It's one complete rotation. Well, the same idea applies to this, and I'm going to add 2 pi to each of these values. However, because it is a fraction, to add them or subtract them, I have to get them into like terms. Okay? I have to get the denominators to be the same. So if I want to find two coterminal angles for 3 pi over 5, I need to convert 2 pi to have a denominator of 5. So if I wanted to add this, I would need to change 2 pi into 10 pi over 5. At this point, the bottoms match, and one coterminal angle in the positive direction would be 13 pi over 5. If I wanted to find a negative angle, I would take the same two values and just subtract them. 10 pi over 5. 3 pi over 5 would be the same as subtract 10 from 3, which would be -7 pi over 5. And I have one positive and one negative coterminal angle. Okay, the same idea applies as a regular coterminal angle with degrees, right? If I have this value, if I really kind of have this certain value that I have, 3 pi over 5, if I want to find two other values for it, once again, I would just add and subtract 2 pi. The only difference is to actually get those values to be the same, I need to get that equal to denominator value, okay? So this kind of leads into the last thing that we're really going to discuss, okay? We want to understand reference triangles, all right? Within each position, we can create a triangle that's going to help us eventually solve values out, okay? And here's kind of the main thing that I want you to think about. A reference triangle really is created based on the angle that you have, okay? But it's always going to be based on the side that is closest to that angle. So for example, if I want to create a actual triangle using letter A here, I can draw a line straight down from my value of P. And if you notice, I have X, Y, and the hypotenuse with a particular angle. This also creates a right angle triangle, which I can use. But how does this work in other quadrants? For example, like letter B, okay? How can I create a triangle out of that? Well, the idea here is that I can create a triangle by using this particular angle. Now, what I can do here is draw that line straight down from P and then assume that this angle here has to be 180 minus whatever angle this is, because it's got to be the leftover value. Then from there, I can just find X, Y, and hypotenuse using those three values. Okay? Down here, it's kind of the same idea. I can create a reference angle here, knowing that this value, my actual angle, is going to be, in this case, since it goes over 180, it's going to be my angle minus 180. Because all I want to do is figure out what this little piece is of that whole entirety of the angle. So I'm going to take away all of this, which is the 180, and whatever left over can create the angle for my triangle. And then last but not least, once again, we're playing this leftover game. If I was in the last quadrant here, I would create an XY triangle, knowing that this value would actually be my angle measure. And that angle measure is just going to be 360 minus whatever your angle is. Because I'm basically saying if 360 is a total rotation, I want to take all of this away to figure out what this particular value inside of it is, or my leftover piece until I get to a full rotation. So once again, that's going to help us kind of derive certain values and help us actually come up with specific answers or specific problems using our trig to actually solve this out. So if I work through this, let's say I was given, they want me to find OP. Okay, so they want me to find this angle right here. Well, to do that, I have to be able to understand this triangle. I'm going to create this value. We have an X value of 3, a Y value of 6. If I want to find the hypotenuse, well, this kind of goes back to an old school thing, Pythagorean theorem. A squared plus B squared equals C squared. In case this is my C. This becomes 3 squared plus 6 squared equals C squared. 9 plus 36. Or in other words, C is going to be the square root of 45, which simplified is going to be 3 square root of 5. Okay? So I can always find these values. If I were to continue on, I can do this at any point. Same thing would be applied here. X would be -4, Y would be 3, and I could work it out in that value. In this case, they want me to find this value, find X for letter C. If I was going to work this value out, oops, excuse me. If I was going to work this value out, they tell me what OP is equal to. It's going to be 6. I know my y is -5, and I would work pretty much the same idea, except now I'd be missing a squared. I would work out b squared, which is -5 squared, equals 6 squared. And I could simplify that out and get to a particular answer. Okay, so if you notice, I can use a reference triangle to kind of help me out. Let's say if I was talking, what if I wanted to actually apply the angle with it? Okay, let's say I wanted to actually use the angle to my advantage. All right, well, explain how you could find each coordinate of P, which basically means if I want to find P, I need to be able to find X and Y, correct? Well, I know my hypotenuse is going to be 12. I know my angle measure is 75 degrees. I can draw my triangle here, and then I could use my sine and cosine to help me work this out. Okay? If this is my angle here, X is always going to be my adjacent side to this angle. So this would be cosine of 75 equals my opposite, or excuse me, my adjacent, which is X, over my hypotenuse. Multiply the 12 over. This would be 12 cosine of 75 equals X. I would work that out to get an answer of... Oops. If I can find it here. Hold on, I gotta get my calculator out. Turns out to be 3.1. And then I would just do the same thing with my y, but now I'm going to use opposite over adjacent. So that's my sine. Sine of 75 equals the opposite, which is y, the opposite angle of 75, or the opposite side, over 12. Multiply that 12 over to get 12 sine 75 equals y. And if I work that out, got to plug that into the calculator, which is about 11.6. So I can find these values using my reference triangle and understanding that I can use my trig to really work out each and every one of these. Okay. Now we'll be discussing this a little bit deeper in class, but that is the end of the video. If you have any questions, bring them in and we'll kind of discuss them. Besides that, have a great day.